Good afternoon to all of you. Today we will discuss about improper integral and its convergence, which is the concept of engineering mathematics, particularly in calculus for the first year student in GTU syllabus. Slide please. So this is the concept, improper integral and its convergence. There are 5 subtopics in this concept. First is classification of integrals. Next is concept of improper integrals. Next is types of improper integrals. Next is types of improper integrals. Next is convergence of improper integrals. And last is examples of improper integrals. We will study about all these topics in this session. Slide. So first topic is classification of integral. Here we had classified the integrals into mainly 2 parts, definite integral and indefinite integral. Now improper integral is actually definite integral has 2 parts, proper integral and improper integrals. Let us try to understand this chart by examples. Definite integration. Definite integration means integration of this form, integration of f of x with respect to x from a to b. Here in the integration limits are present from a to b, then this type of integration is known as definite integrations. And indefinite integration, indefinite integration means integration in which there is no upper and lower limit for the integration. So this type of integrations are known as indefinite integration. Again, this definite integration has 2 parts, proper integration and improper integral. Proper integrals means you see here this is the proper integral if a and b are finite numbers as well as function f of x is continuous inside the interval, closed interval a to b. Okay, so this is the proper integral. While improper integral, inside the improper integral there is no guarantee that in this integration a to b f of x dx a and b both will be finite numbers as well as function f of x is continuous. So improper integral is one part of the definite integration. Next slide. You see here improper integrals. We know that integrals of the form integration of f of x from a to b dx are known as definite integrals. Here f of x is continuous on closed interval ab as well as a and b are finite numbers. Now we think about different situation when f of x is discontinuous on closed interval ab and a or b or both are not finite numbers, then above integration of f of x from a to b is known as improper integral. What it want to say is, it want to say is that if we have integration from a to b of some function f of x and if a and b both are finite numbers and function f of x is continuous inside the interval ab, then this type of integrals are known as definite integrals or proper integrals. But if we think about the different situation, means if we have a or b are infinite numbers as well as function f of x is discontinuous inside this interval a b, then this integral becomes improper integration. Next is types of improper integrals. Here we shall classify the improper integrals into following three types. Next slide. First kind improper integrals. First kind improper integrals. An integral f of x dx from a to b is said to be improper integral of first kind if either or both limits are infinity. Here the examples, first example is integration from minus infinity to b x square dx. You see here lower limit of integration is minus infinity, so it is improper integral. Second example, integration from 1 to infinity of 1 upon x square, 1 upon 1 plus x square dx. Here upper limit is infinite, so this is improper integral. And third is both limits are infinite. So you see here third example is integration from minus infinity to plus infinity x cube plus 2 dx. So both limits, upper and lower limits, are infinity, so it is improper integral of first kind. Okay. Next is second kind of improper integrals. An integral is said to be improper integral of second kind if the function f of x is somewhere discontinuous on closed interval a b. Here first example is integration from minus 1 to plus 2 1 upon x square dx. So you observe that this function 1 upon x square is discontinuous at point x is equal to 0, and 0 lies in between minus 1 and 2. So function is discontinuous inside the interval minus 1 to 2. So it belongs to the second kind of improper integral. Next example is integration from 0 to pi of 10x. Here if we take x is equal to pi by 2, then 10 pi by 2 is infinity. So function is discontinuous at this point, and hence it belongs to the second kind of improper integral. Next type is a third kind of improper integrals. An integral of the form integration from a to b f of x dx is said to be improper integral of third kind if either or both limits are infinity. That means it is of first kind improper integral. And next is, and the function is discontinuous somewhere in closed interval a b. It says that integral is also of second kind. Here the first example is given that integration from minus infinity to 0 sec x dx. So you see here lower limit is minus infinity, so it belongs to the first kind of improper integrals, as well as sec x is discontinuous at minus pi by 2. If we take minus pi by 2 from this interval, then we have sec x is discontinuous at minus pi by 2. So it also belongs to the second category, I mean in the second kind of improper integral. That's why it is of third kind improper integral. Similarly, the second example is integration from 0 to infinity ln of x dx. Here function is discontinuous at 0 as well as infinity, and limit of integration is also infinity. So this integral has both kind, first kind and second kind of improper integral, so it is third kind of improper integral. Next, here stated the fundamental theorem of integral calculus. Fundamental theorem of integral calculus is necessary to study the concept of improper integral. What is that? It is stated here, if f of x is any continuous function on closed interval a b and capital F of x is an antiderivative of small f of x, then integration from a to b small f of x dx is equal to capital F of b minus capital F of a. Here let us try to understand the word antiderivative. antiderivative. A function capital F of x is said to be an antiderivative of some another function small f of x if capital F dash of x is equal to small f of x. Antiderivative is actually nothing but integration. It is another name of integration. So definition want to say is if capital F is some function and small f of x is another function, then we say capital F is an antiderivative or integration of this small f if capital F dash of x is equal to small f of x. So if I let capital F of x is equal to x cube by 3 and small f of x is equal to x square, then see that capital F dash of x is differentiation of this function capital F of x with respect to x is 3x square by 3. It is nothing but x square, and x square is small f of x. So we have capital F dash of x is equal to small f of x. Thus by definition we say that this x cube by 3 is an antiderivative of this function x square. Okay, because and we know that integration of x square dx is x cube by 3. So it is nothing but the antiderivative. Antiderivative means integration. So in the fundamental theorem of integral calculus, if we have capital F of x is an antiderivative of small f of x and small f of x is in continuous on closed interval a b, then we have this relation integration from a to b f of x dx is equal to capital F of b minus capital F of a. Let us try to understand how we can solve the examples using fundamental theorem of integral calculus. Suppose we have an integration from 1 to 2 x cube dx. So to apply the fundamental theorem we should have one necessary condition is that f of x is continuous on closed interval ab. So you see here function f of x is equal to here x cube is continuous in the interval 1 to 2. So we can apply the fundamental theorem. So we can get the answer using fundamental theorem of this integration by this formula. Capital F of b means here capital F of 2 and capital F of a means here capital F of 1. Now question is how what is the capital F of x? That means what is an antiderivative of this x cube? Antiderivative means integration. So integration of this function is nothing but x raised to 4 by 4. So we have now capital F of x and we can find the answer of this integration by finding capital F of 2 minus capital F of 1. So this is same as capital here capital F of x is now x raised to 4 by 4. So this is 2 raised to 4 by 4 minus 1 raised to 4 by 4 is equal to 16 by 4 minus 1 by 4 is equal to 15 by 4. So by this way we can find the answer of any integration. Next, here given a problem, can we evaluate integration from 0 to 4 1 upon under root x minus 3 dx directly? Then answer is no, because here function f of x is 1 upon root x minus 3. If you put x is equal to 3 in this function, here denominator is 0, hence the function becomes infinity at the point x is equal to 3. That means function is not continuous on closed interval 0 to 4. So we can't apply the fundamental theorem of integral calculus. So we cannot evaluate it directly. Next, before studying the examples of improper integral, here we want to discuss about the limit form of the improper integral. Here first statement is, if small f of x is any continuous function on closed interval a to infinity, then integration of f of x from a to infinity is equal to limit c tends to infinity integration from a to c f of x dx. What it want to say is, let us try to understand. We have f of x is continuous on closed interval a to infinity, then integration from a to infinity f of x dx is equal to limit c tends to infinity integration a to c f of x dx. Let us try to understand this formula using the graph x-axis, y-axis. Let f of x is any function whose graph is something like this. Okay, this is graph of y is equal to f of x. Here interval of integration is from a to infinity. Suppose point A is somewhere here, and we know that in this direction there will be infinity. So our interval of integration is from a to infinity, but we here we let some point c in this interval a to infinity. Suppose point c is somewhere here. Now we have two intervals from a to c and c to infinity. So actually this interval a to infinity is now from a to c and c to infinity. Now integration here given is from a to infinity. So integration from a to infinity f of x dx is equal to, what we can do, first we evaluate integration in between these 2 points only from a to c. Thus we take integration over a to c only of the function f of x. Okay, and then we apply the concept of limit. That means we extend this point c towards infinity using the